Thank you very much. So this is a part of our cryptography primer, our overall cryptography primer, which is a e-masters course. This is just going over the symmetric part of it. So we start off with symmetric cryptography. Other terms for symmetric cryptography would be secret key, shared key, single key, parent key. All of these terms, when you hear them, you should think of symmetric cryptography. Symmetric cryptography essentially means that you have identical keys, the same key on both sides. If you can imagine two people, Alice and Bob. Alice goes off to a hardware store and buys a lockbox. And this lockbox comes with two identical keys. She gives one to Bob, and now Bob has the same identical key. And then they can use this box to go back and forth to send secrets back and forth to each other. And nobody else can see those secrets except each other. So the way they share the key is called a key establishment, and the way they share it is the simplest way of key establishment of all, and it's called key transport, because Alice essentially just transports the key to Bob. She gives the key to Bob, and this is the simplest form of key establishment. She knows, or I should say Bob knows and trusts Alice, so he inherently trusts the key. I mean, since they know and trust each other, Bob has no reason to believe Alice would give him an erroneous key, right? The fundamental thing about symmetric key is the keys need to remain secure. This is paramount. The vulnerability of symmetric key is the confidentiality of that key. There's a couple of questions you need to ask. Are there multiple copies of the key? Maybe Alice doesn't know there's multiple copies. Maybe the manufacturer of that lockbox made more than just two copies of that key. That would be awful, right? Was the exchange secure? When Alice gave Bob that key, it needs to be under sort of an umbrella of relative security. She needs to make sure, or they both need to make sure, that nobody was able to get any information about that key. No pictures, no imprints, no anything. So it has to be a secure exchange. Also important is, does Bob value the key as much as Alice? Alice went off and went through all of this effort to get this lockbox and to get these keys and to exchange these keys securely with Bob. But is she sure that Bob cares as much as she does about the secrets that she's about to exchange with Bob? Because if he doesn't, if he is careless with that key, then the entire system is ruined, right? Is there someone Alice and Bob trusts with the key but shouldn't? This is another thing. Is there a third party that they decide to also share the key with, but they shouldn't do? That's also a big problem. Secret key or symmetric cryptography can be extremely secure, but great care must go into protecting that shared key. Secret keys are need to know only, and the number of copies should be aggressively managed. You shouldn't just wallpaper the world with these keys. In fact, one of the things that we say in the crypto primer is later on in the crypto primer is when we talk about when you should pick between symmetric cryptography and asymmetric cryptography, and we're not talking about the asymmetric today, but when you should pick between the two. A perfect time to pick symmetric cryptography is when your system is completely enclosed and it's all yours. The network is only yours. Because then there is no Bob, there's only Alice, and there's no other party that could possibly compromise the key. So let's talk about a hash function. A hash function is a building block of all cryptography. A hash function uses a strong, irreversible mathematical transformation. The characteristics of a strong crypto hash are it's easy to compute a digest. It's infeasible to regenerate the original message. It's infeasible to modify a message without changing the digest. It's infeasible to find different messages with the same digest. And the output of a hash is called a message digest, and it's of fixed length. It's usually of the same length as is the input. And most engineers have come across digest, or I should say hashes before. It's if you're familiar with CRCs, cyclic redundancy characters, that's a hash. But that hash is far too weak to be used with cryptography. So other mathematical compression algorithms, and that's what a hash is called, a compression algorithm. Other stronger compression algorithms have been formulated for cryptography specifically, and like SHA-256 is one of them, which is part of the SHA-2 family. And again, a hash function gives a fixed output. So if you put a 1 kilobyte file into it, you get a 32-byte message digest out of it. If you put a 1 megabyte file into it, you get a 32-byte message digest out of it. If you put a 1 gigabyte file into it, guess what? You get a 32-byte message digest out of it. So let's use hash in symmetric authentication. And let's consider the scenario where Alice wants to authenticate a connection with Bob. And Bob knows and trusts Alice, and they both have copies of the same identical key. So the first thing that Alice does is she sends Bob a random challenge. And Bob receives that challenge. And this is not a secure connection. So there could be thousands of adversaries that could be listening in on that random number that she sends to Bob. But then Alice and Bob both hash that number with the shared key that they both have. And then Bob sends back the result of that hash, that digest, back to Alice. So those adversaries, again, over the same connection. So those adversaries first see a random number go across, and it means nothing to them. It has no value. And then they see this digest come back, and that digest looks just like another random number. It has no value to them. But it does have value to Alice, because Alice is waiting for that particular digest, because she's calculated that exact same number. And what she does is a binary compare against the digest that she calculated against the number that Bob returns. And she says, okay, I'm connected to Bob. I know of all the people that might be listening to me out there, at least I'm connected to Bob. So she knows she has a connection to Bob. And that has value. And so she's authenticated that Bob's out there. Now, this is incredibly important. All communications between any two entities have to start off with an authentication. Now, just for time's sake, as we go through presentations in cryptography, we don't keep repeating this idea. So I want to say that as we talk about these functions, it should be assumed any communications first start with an authentication. Okay, so whenever two entities begin communicating, first they authenticate, and then they continue to do what they need to do. So let's use that example in a real-world system. We're going to make believe we are a computer maker, a notebook computer maker, and we also make our own batteries. And we don't license any third parties to use to make batteries for us. So let's consider how we provision these batteries for use in our notebooks, so that no other party can make batteries for our notebooks, because we've all heard about those situations where LiPo batteries go on fire, and we don't want to have that liability. We only want people to use our batteries because we know they're safe. So we start off with a parent key from the headquarters, and we have a manufacturing line on the manufacturing line is a hardware security module, and we're on that manufacturing line, we're going to make batteries. On that same manufacturing line, we are also going to make our notebook computers. And our batteries we can call our disposable device, because you're going to use up a battery after a while, right? And our notebook we're going to call the host. And our notebook has this thing in it called a TPM. That's a trusted platform module. Easy for me to say. So that's essentially another little hardware security module that's inside of every notebook computer. Every notebook computer has it. You can't run Windows 10 without it. So it's a hardware-based, persistent, secure vault inside all notebook computers, where secrets are held, and it's infeasible to really hack and get secrets out of it. So this is what we start off with. We start off with the parent key. from the HQ, and we have the manufacturing line and the two things that we're going to make on the manufacturing line. So the headquarters puts the parent key into the hardware security module, which is another hardware-based persistent secure device. And so now that manufacturing line has possession of the parent key, and nobody working at that manufacturer has access to that parent key. That's locked inside that device. And that manufacturing line is going to start making batteries. And the first thing it does is it asks the battery for its unique serial number. That serial number goes over to the hardware security module. And inside that security module, the unique serial number gets hashed with the parent key, creating a derived key. That derived key is unique to the battery. And that derived key gets injected back into the battery. And also on that manufacturing line, that parent key is securely injected into the TPM of the notebook. And this all happens on the battery. I'm sorry, on the manufacturing line. Now, by the way, if any of you have questions, please text them to Megan, and she'll ask me so that I can answer them as we go, because this presentation sort of builds on itself. So if there's any kind of confusion, you'll just have sort of a cascade problem. All right. So if anyone has any questions, you should ask. So this is what happens in the factory. In the next slide, we'll go over what happens in somebody's living room when they buy a battery and they put it into the notebook. So now we're in somebody's living room and or kitchen, and they have their notebook computer, and they just came back from some store with their battery, and they put the battery inside the notebook. And the first thing the notebook has to do is check to see if the battery is genuine, because it's not going to start charging this battery unless it is. Now, inside the notebook computer, of course, we have the parent key, and inside the battery, we have the unique derived key that was made at the factory. So the notebook computer first asks for the unique serial number of the battery. And since it has possession of the parent key, it's capable of creating, or recreating, I should say, the derived key that was made for the battery. Once it has the derived key that was made for the battery, it doesn't just go ahead and ask for the derived key from the battery. That's not secure, right? You don't want to reveal that battery. You never use keys directly. You always use keys indirectly. So the notebook computer is going to create a random number and send that random number over to the battery and ask the battery to hash the derived key with the random number, which would create a digest, and send that digest back to the notebook. The notebook will do the same thing on its side. It will hash the derived key with that same random challenge, creating hopefully an identical digest, and then the notebook will do a binary compare against the returned digest from the battery and the digest it created. And if it matches, it knows that the battery is genuine. And then it will start charging the battery, and everything will be fine. So that was identity authentication. So now let's go and use hash for message authentication. So now let's assume that Bob wants authentication that a message came from Alice. And of course, same deal goes. Alice and Bob know and trust each other, and they have the same shared key. So this time, Alice generates a message and sends it off to Bob. Bob takes that message and puts it on the side. He doesn't know it's really from Alice and genuine yet, so he's not going to even read it yet. Then Alice and Bob both hash the message along with the shared key. They simply put the key through first and then put the message through second, and just concatenate the two. A hash, even though this box looks like it has two inputs, a hash really only has one input and one output. So anything you put into a hash, you concatenate. You just line it up in a queue and put them through one at a time. And then the output is the digest, right? So Alice and Bob go ahead and hash the two together, and then Alice sends the digest to Bob. Now, in this case, since it is called, since the digest is authenticating a message, we give it a different name. It's called a message authentication code, and a MAC. And Bob does the same thing that Alice did before. He does a binary compare against his calculation versus what Alice calculated. Now, and if it matches, then he knows that the message came from Alice, and hopefully nobody else but Alice, because Alice should be the only other person with that shared key in the world, so it should have only come from Alice. Now, one thing I want to point out, again, this connection here, the connection between Alice and Bob for the message, and the connection down below where you see message authentication code, this is not a secure connection. You could have adversaries listening and everything. And again, both of these things look like random numbers. When I showed you this, it looked like I sent two different messages. I probably didn't, or Alice probably didn't. What she probably did was she made the message, then she hashed it, created the message authentication code, attached the message authentication code with the original message, and then sent it in one payload off to Bob. Then Bob stripped out the message authentication code, hashed the message alone, recreating the message authentication code, binary compared the MAC, and then said, okay, now I can read the message. Okay, so it's not two actions here, even though this block diagram looked like it. All right, so symmetric cryptography to generate session keys. What is a session key? A session key is used with a cipher to obfuscate messages and data. So when we encrypt, we use what's called a cipher, and ciphers need keys. And a cipher is a math function which uses a unique key to uniquely obfuscate input, and we call that input clear text. And we turn that input into something unreadable, which we call ciphertext. And there's many types of ciphers, and you've probably heard of many of these. Advanced Encryption Standard, which is called AES, the Data Encryption Standard, which is called DES, and then DES turned out to be not strong enough, so they did it 3 times in a row, which is essentially what triple DES is. And that's what triple data encryption standard is, and they call it 3 DES or triple DES. And then there's Blowfish, Twofish, International Data Encryption Algorithm, IDEA, and ChaCha20, and so forth. Ciphers also have modes of operation. So block ciphers like AES and DES, you could have you string them together in different formats. We have a whole presentation on this. We go over all the different ways of stringing these block ciphers together. In all these different unique ways of creating encryption, but it's usually something like AES dash something. Like in this case, I'm showing AES CBC for cipher block chaining, and then there's also AES dash GCM for Galois counter mode. So, and also keep in mind that when you use a cipher, if you create a critical mass of obfuscated text, ciphertext, with the same key, you start running into vulnerabilities. This is known as key exhaustion. You can only use a key so much. After a while, you've created so much ciphertext with that key that you start to create mathematical vulnerabilities that someone can start backward calculating what the key must have been, because all of these ciphers are well known. The mathematical nature of these ciphers are well known. They're very complex and they're very difficult to run backward. But once you have an enormous amount of ciphertext, you kind of can. I'm really fuzzing over this. It's you can look it up in Google, but it's called key exhaustion, and you don't really want to make too much. So with like Galois counter mode, you really don't want to 2 to the 32 is really the number where you want to stop making ciphertext, and you want to change that key to something else and then make more. All right. So you want to change the key, and then when you change the key, you're creating what we call a new session, and hence the term session keys. And how often you change that session depends on your use case. If you have this little IoT device that only puts out a few bytes of data each day, well, you probably never have to change the session. You probably never have to change the key for the lifetime of the device. But if you have something that's putting out video and gigabytes of data each day, then you're going to have to change that session key a lot. And if you're in the military or financial world, you're probably going to change that session key quite a bit just for enhanced security. Those guys sometimes change the session key every 100 milliseconds. And if you can imagine that, that's right. They're changing the key in the middle of a transmission. So as they're sending a message, they're rotating the key while the message is still being sent every 100 milliseconds. So symmetric cryptography for session keys. So let's say Alice wants to send Bob a secret message, and Alice and Bob have previously shared an identical secret key. So Alice sends a random seed to Bob, random number. They both hash this random number with the shared key that they both have, and they create this derived key. So this all looked familiar up until they created this derived key, right? So they're not going to share the output of this hash this time. They're going to hold the digest of this hash close, as a secret, and they're going to call that their derived key. That's their session key. They're going to use that as their session key, and they're going to use that with their cipher. And Alice is going to turn the plain text into ciphertext, send the ciphertext to Bob, and then Bob is going to use that derived key to turn that ciphertext back into plain text. And again, depending on how much plain text is turned into ciphertext with that key, they're going to decide to change the key. So what did we just cover? We just covered what symmetric cryptography is. That was it. We covered the simplest form of key establishment, which is called key transport, where Alice simply gives the key to Bob. She just transports it to Bob. We went over what a hash function does, how identity authentication is accomplished with symmetric cryptography. Basically, the identity is by Alice sharing the key only with Bob and nobody else on the planet. When Bob authenticates with Alice, she knows that it's Bob. That's how Bob's identity is established. How message authentication is accomplished using symmetric cryptography. We did that by sending the message and then a message authentication code. We talked about what a cipher is and why we shouldn't use the same key over and over again with a cipher and make too much ciphertext with it. And we talked about what a session key is and how to spawn one with symmetric cryptography. Okay, I spoke rather fast. I hope not too fast for people. I am from New York. I apologize.
No, perfect timing. I just want to thank everyone for joining us today. We hope you found the session informative. Be sure to visit www.microchip.com/shieldsup to view all upcoming sessions and watch past presentations on demand. Be sure to also follow us on LinkedIn, Facebook, Twitter, and Instagram, and YouTube for the latest news and updates. Thanks again for your time, and we hope to see you during our next session. Have a great rest of your day.